If you trust the title of the report this presentation is based on, you'd probably think it is seemingly about autonomous vehicles and logistics, and not much else. However, that would do an injustice to the heart of what is covered. It seems that most people consistently misjudge not only their grasp of certain facts regarding technology, but the impact and age of that technology as well as the speed of its development. For example, many people might agree that Tesla Motors is groundbreaking. But is it really? The first electric cars were operational in 1883, and by the first decade of the 20th century, roughly a third of all automobiles on the streets of New York City were electric. The batteries that Tesla uses are basically variations of what the laptop industry has used for years. Even their autonomous vehicle tests are not new because GM, RCA, and the British government, among others, tested self-driving car systems in the late 1950s and early 60s. The point being that what appears to be new and marvelous ideas are often only new and marvelous because few of us have taken the time to educate ourselves on those ideas instead of just following the hype. My name is Ron Heath, and I hope to shed some light on the history of the development of autonomous vehicles and something of where that development fits into their future in logistics. One of the first examples of autonomy in a vehicle dates back to Greece, circa 60 AD. Carts were used to carry actors to and from stage. These carts used weights suspended from a rope to travel forward or backward a predetermined distance. The next development would occur roughly 1400 years later when Leonardo da Vinci invented a stage cart that would also turn at a predefined distance. Though it's accurate to say that the implementation of autonomous vehicles is very old, the idea predates the existence of the most rudimentary ones by several hundred years. In fact, the idea dates back nearly 3,000 years. However, the problem with autonomous vehicle development, as with nearly every field of human endeavor since the dawn of man, is that what we wish to do and what we know how to do seldom coincide. The technologies or ideas on how to implement it in innovative new ways often lags by years, if not centuries, and they are often reapplications of another technology. An example of that, which relates to vehicles, is that the first car was developed as a steam-powered engine around 1769. And in fact, the first internal combustion engine was patented approximately 2 to 3 decades later, but it took nearly 100 years after that to develop an internal combustion-powered car. It then took an additional 60 or 70 years before cruise control was patented for the car. However, when the first steam locomotives were invented, they had a system similar to cruise control to govern wheel speed. Thus, the cruise control, which was patented in the middle of the 20th century and didn't become standard for several decades, was just a reapplication of an 18th century invention. In fact, it's entirely possible that some of the solutions for future autonomous vehicle problems already exist in some other form and are merely awaiting repurposing. I'll give a couple of examples, which are not related to autonomous vehicles, but will illustrate how a thing is created and then much later a new purpose that was totally unforeseen occurs, which allows for a new advancement. Before I studied logistics, I studied to be a machinist. One of the tools we used every day to measure parts is called a micrometer. For all of its complexity and utilitarian purpose, at its heart, it's just a nut and a bolt. About 2,200 years ago, Archimedes came up with the idea for the screw thread, which is the thread which makes a bolt into a bolt instead of just being a metal rod. Technically, the idea of the micrometer could have been hatched that same day and it would have worked. Only he invented it to move water up an incline, and it took another approximately 1,900 years for it to find a purpose as a measuring tool. Only it was used to measure the focal size of celestial objects in a telescope. Great if you're an astronomer, but not much use otherwise. It wasn't repurposed for its current use for measuring parts for another 200 years. The other example is Gorilla Glass, which was a research project whose results sat patiently on a shelf at Corning Glass from about 1960 until 2005, when Apple expressed an interest in a strong, thin glass to be used on the iPhone. The story of autonomous vehicles is replete with similar examples of the one set of developments awaiting the rest of the technology to catch up. However, many ideas that are over half a century old have caught on or are catching on, even if not in the forms originally envisioned, such as the Firebird 2 concept car of 1956, which introduced many futuristic features, including what GM hoped would be part of the future of the automotive industry: self-driving cars that relied on a smart highway, which had embedded electric wires in them to send signals to cars driving on them. In fact, from the mid-1950s until as recently as the late 1970s or early 1980s, various projects were being pursued to create self-driving cars that utilized smart highways. However, the idea failed to gain traction due to the cost and presumably the fact that it makes more sense once the technology was available to create cars that relied on their own technology rather than relying on special roads with strips embedded in them. For one, the cost of the autonomous vehicle is not a collective cost, whereas a smart highway would require taxpayer funding. Thus, if individuals desire an autonomous vehicle, they purchase it, as opposed to municipalities, states, or the federal government having to find funding to convert to smart roads. Whether we're talking about drones, autonomous cars, or ships, portions of the technology required for them to operate have existed for some time, but we're waiting for other portions to be invented, implemented, or converted to the required purposes. As an example, in the last decade of the 19th century, Nikola Tesla demonstrated a radio-controlled boat which he envisioned helping the Navy to eventually have somewhat autonomous torpedoes. But as early as a few decades before that, the predecessor of the modern homing torpedoes was introduced. The U.S. Navy has used drones as targets in the late 1940s and early 1950s. Many technologies that most of us consider modern or recent developments are simply derivatives of technologies that date back to the final decades of the 19th century or earlier, with a few dating to the first decades of the 20th century. As an example, the original idea for the first altimeters predates aircraft, as the idea was originally used to maintain depth in a type of torpedo created in the mid-19th century. Autopilot for aircraft has existed since the 1930s, and yet planes routinely do not use it to take off or land. In fact, future plans for unmanned cargo air vehicles would have a single operator controlling the takeoff and landings of as many as 10 vehicles, which would otherwise fly autonomously to their destinations. Also, while much of what is mentioned in this presentation refers to autonomous cars, the technology to make a passenger vehicle autonomous versus a cargo vehicle autonomous, well, it's all the same thing. For the purposes of addressing autonomous vehicle usage in logistics, it is obviously necessary to develop technologies which often are used on light passenger vehicles before they're used on other vehicles. For instance, for a tractor-trailer rig to be able to be platooned without a driver independently controlling each vehicle requires adaptive cruise control so that the truck can understand the gap and speed it needs to maintain. For that technology to exist, it required not only the invention of cruise control, but also the discovery of radio waves, the invention of radar and LiDAR, which uses light instead of radio waves. It also required the invention of various sensor arrays and the electronics and computer hardware to receive, interpret, and process the data about the driving environment. Even after those technologies were invented, they had to be made small enough, rugged enough, and inexpensive enough to be placed in consumer vehicles. To put this into the proper perspective, Google has spent in excess of $1 billion developing autonomous cars. In fact, several car makers have spent comparable sums. The original concept cars were part of a DARPA project. And they're the same people that invented the internet and the GPS, among other things. But the problem was, and still is, that the technology is prohibitively expensive. In 2017, the cost to convert a light passenger vehicle to be autonomous was something like $250,000. And even then, it would only be self-driving under specific circumstances rather than all circumstances. In fact, Mercedes is developing autonomous vehicles, and theirs disengage from autonomous mode about 700 or 800 times per 1,000 miles driven. Granted, Google has a better track record, but theirs also disengaged, albeit only about 70 times per 1,000 miles. But what is important to note is that what most people expect and what some of the vehicle manufacturers are promising is a level 4 or level 5 autonomous vehicle. The problem is that level 5 autonomous vehicles are defined as ones that require no human aboard. Yet the very best autonomous vehicles today still require a human driver at least 70 times per 1,000 miles, and the rest require them even more frequently. What we're mostly seeing are between levels 1 and 3 in autonomous vehicles, which are driver assist all the way up to limited control by the vehicle. For instance, the vehicles can maintain lanes and speeds or change speeds. They just can't do that inside of a city, and therefore require human drivers once they enter urban areas. But what we're seeing are issues where the programming for autonomous vehicles is not yet up to the task of reacting to chaotic environments such as busy urban streets filled with pedestrians and complicated traffic patterns where vehicles are turning in front of the autonomous vehicle, merging into traffic with them, and doing other unexpected things. Also, it is not that the programming won't exist or that it doesn't already to some degree exist now. It is more that it is not yet ready to assume 100% control of every mile driven. Now, it's fair to point out that autonomous vehicles exist in logistics. In fact, many do, but they exist almost exclusively in controlled environments. For instance, Caterpillar has produced a series of autonomous heavy dump trucks for the mining industry. In fact, one Australian company is using nearly 200 of them now. But that environment is much more controlled than a city street or even an interstate. Moreover, companies like Seagrid produce autonomous lift trucks for use in warehouses. But again, that is a more controlled environment and the speeds are much lower. In the case of the Seagrid lift trucks, they have in excess of 2 million miles traveled inside those warehouses without a single accident. But they're also not traveling at highway speeds either. But this brings up another point. That point being that while Google and others would be quick to point out that they have tested their product for this many thousands of miles, the statistics on U.S. vehicle fatalities are such that there is about 1 per 100 million miles driven. To put that into perspective, Google has tested their autonomous vehicles in the real world for only about 5 million miles. That sounds like a lot until the sheer magnitude of vehicle traffic on U.S. roads and highways is taken into account. In 2017, vehicles traveled over 3.2 trillion miles on our roadways. Experts estimate that autonomous vehicles won't have much market penetration until after 2030 and likely not until as much as a couple of decades later. A portion of that is directly attributable to several things. First, there's very little, if any, standardization regarding autonomous vehicles, and as such, their performance is not uniform, meaning that some companies have vehicles that perform better in autonomous tests than others. Therefore, until there is more standardization, this is problematic. It is the same issue that the fledgling personal computer industry saw, where buying one brand instead of another led to technical issues because parts, cabling, and programming was all proprietary. Meaning if you picked the wrong one, you could have problems that were difficult if not impossible to remedy, and the same could easily be true of buying the first autonomous vehicles if the technology for the brand purchased is found to be inferior. Second, both Tesla and Uber have experienced fatalities using vehicles in autonomous mode. Yet statistically, 2 fatalities in strictly human-driven cars would have required nearly 200 million miles driven. Yet the combined total of all autonomous car testing in real-world driving is less than 5% of that figure. Before either regulators or the public are going to trust level 5 autonomous driving, it should require considerably more testing than has occurred thus far. Third, there are technical hurdles that have yet to be tackled or even experienced prior to the implementation of widespread level 5 autonomous vehicle usage, whether it's by the consumer or the logistics industry. Fourth, no level 4 or 5 technology exists at present on the market, yet several manufacturers are stating that not only will they have it, but that it will be in vehicles available to consumers sometime during the next year. And in fact, at least one manufacturer redefined what the individual levels of autonomous vehicles actually represent. However, I'd be remiss if I didn't point out that during the 1950s, car makers were saying we were less than a decade away from autonomous electric-powered vehicles. Well, obviously, we still don't have them. The point being that it's very difficult to have the level of prescience required to accurately forecast when and as of yet undeveloped technology would not only be invented, but be tested and refined to the point that it was ready for the consumer. This is especially true where a byproduct of a product failure includes the potential death of that consumer. Fifth, technology and the progress of it has routinely been overhyped regarding timelines or impacts, with many things being spoken of as groundbreaking, yet historically many groundbreaking technologies were considered nigh on useless at the time of their invention or discovery, while others were overblown. None of this should be interpreted to say that autonomous vehicle usage in logistics isn't presently being done, or that in the future it will not represent a major portion of vehicle usage in general. However, it is more of a cautionary statement regarding concerns of a massive upheaval in both the labor markets due to autonomous vehicles and in how logistics is handled, neither of which is an immediate concern. In fact, according to experts, such a scenario would not occur to any major degree for at least another generation. Although what is being discussed more often is something called a multiplicity, where automation and autonomous vehicles enhance human efforts rather than replacing them completely. Considering the meager beginnings of autonomous vehicle development has come a long way since the first stage cart in Greece. However, the progress has been slow, and it's not yet complete to the extent that truly autonomous vehicles, that is to say level 5 autonomy, is not on the immediate horizon. For one, there's much still to be done, and what once took centuries or decades to invent or innovate now takes years instead. But that doesn't negate the fact that some of the programming and computing needs have yet to be met. However, this brings up an intriguing point. Autonomous vehicles generate vast amounts of data very rapidly. In order to handle this data and to achieve the necessary throughput of it, that will require a great many advancements in computers and computer science. The advances required to handle the bandwidth required for that data, the computational requirements, and other aspects will undoubtedly have a ripple effect throughout the rest of the economy and technological sectors of various markets. Additionally, many of the projects being tested or conceptualized are intriguing in their possible applications. Some have great potential, including possibilities that have yet to even be discussed or considered, with many possibilities outside of merely logistical applications. For instance, Boeing has been developing what might be considered a heavy lift electronic drone. By regular aircraft standards, it's nothing special because it can only carry a payload of between 1/4 and 1/2 ton and only for about 20 or so miles. However, it's not difficult to imagine these drones being used to resupply ships which could not otherwise anchor, or to resupply remote islands without the requirement of the ship stopping. For example, Pitcairn Island in the Pacific requires freighters to bring them mail, drop off supplies, and pick up or drop off trade goods, while the ships sometimes takes on supplies of fresh fruits or fish while anchored offshore. However, by using drones with a range of dozens of miles, it would be possible for the ship and the island to exchange a pair of drones that are loaded with cargo, all without the ship being forced to stop, slow down, or come closer than a dozen miles from shore. Furthermore, drones such as those could deliver emergency medical supplies to areas that have experienced a natural disaster, or even carry small generators to areas without power, such as Puerto Rico after the storms last year. Moreover, a drone of that type of lift capacity could effect seaborne rescues if required, or perform a multitude of useful functions that would otherwise require a helicopter and a crew along with a much larger landing area. Thus, the drone could lessen the manpower and resources required to perform several important functions. Additionally, in the Netherlands, there is an electric-powered container ship that should begin testing in semi-autonomous mode in 2020 and is expected to be fully autonomous not long afterwards. One of the immediate impacts of that autonomous vessel is that it is expected to reduce heavy truck traffic on a short stretch of coastal road in the area where it's being tested, and thereby reduce the emissions by those trucks to a substantial degree. Also, it will facilitate safer traffic. However, if the idea were scaled up and were seen to be feasible, it is not unforeseeable that autonomous vessels could be used to transport goods between distant ports of call. One of the possible benefits of the implementation of autonomous vessels might be to reduce the incidence of piracy in areas such as off the coast of Somalia, among other areas. After all, it would require pirates with a more technical skill set than what is currently seen in that area. Thus, it could reduce insurance costs for many vessels due to a reduction in accidents or instances of piracy, among other problems. However, the vast majority of experts in the field do not feel that the technology will be widely embraced to the point of replacing human crews for the better part of a generation. Obviously, any reluctance on their part is understandable. Container vessels and tankers represent a huge outlay of capital, and who would want to trust several million or hundreds of millions in resources to a technology that may or may not be up to the task? Furthermore, the way one discovers the weakness of a system such as that is likely when they receive a midnight call either informing them that it performed well or that $400 million of steel that used to be their ship is now sitting on the bottom of the ocean along with its cargo. Whereas individuals may be early adapters of any technology that is newly touted as the next great thing, businesses tend to be more pragmatic in how much money they entrust to something not completely proven. As logisticians, we learn that we must justify expenditures. We must seek certainty to the degree possible. However, while many technologies hold great potential, they can equally be fraught with danger, as witnessed by the new anti-stall control systems in the Boeing 737 MAX, which were meant to prevent crashes, but actually caused crashes that otherwise would not have happened. Thus, it is understandable that a certain degree of reluctance to completely turn over valuable assets to autonomous control would exist, not only in the immediate, but the foreseeable future as well. Furthermore, the possibility of a vehicle being hacked to deliberately crash it is also likely a major concern, or should be if it's not. Thus, we should all expect that one byproduct of autonomous vehicles is likely to be enhancements to cybersecurity, In fact, one indicator of how much companies fear flaws in IT security is witnessed by the fact that Microsoft spends over $1 billion annually on cyber and network security, and yet they still have problems from time to time. Additionally, considering that the sensors on Tesla's self-driving cars can be spoofed into either registering non-existent threats or failing to see real ones, you can see where this would be a problem. However, once any reasonable or unreasonable concerns over possible safety are out of the way, another intriguing application of or for autonomous vehicles is in the area of unmanned aerial cargo vehicles. These aircraft could easily fill a void that currently exists in shipping. They can fly faster than a cargo ship can travel, and while they're slower than a jetliner, they could be sent to places that might not otherwise have air transport. Moreover, oddly enough, they straddle a niche all their own. A lot of air transport is in the cargo area of commercial airliners, so they help add an extra revenue stream to commercial passenger flights. However, in the absence of an already scheduled flight, these jets are a more expensive form of transport than unmanned aerial cargo vehicles. Thus, they can serve areas that are underserved by air transport and do it cheaper than a normal aircraft, while obviously doing it faster than a cargo vessel. Making a flight from China to almost anywhere in Europe is less than a day of continuous flight. Moreover, some of these craft are being envisioned to have a payload of up to 20 tons and a range in excess of 5,000 miles. Indeed, much of what I've discussed are current or near-term projects or possibilities. However, the further development of autonomous vehicles offers a variety of usages in the future which might be worth exploring. For instance, I can see some of the autonomous vehicle projects having far-ranging applications as the U.S. and other nations begin work on a proposed lunar base, which is supposed to take place within the next decade in preparation for manned Mars missions. In fact, one of the major impetus behind some of the initial autonomous vehicle research revolved around questions of how an autonomous rover might react during the first manned and unmanned lunar missions. Research was ongoing at Stanford University from about 1960 to 1986, which resulted in a great deal of practical solutions and innovation regarding autonomous vehicles. Given the constraints of the operating environments involved and the ability to utilize autonomous vehicles to extract resources, explore, or transport materials and personnel on the lunar surface, on Mars, or even in Antarctica, that could prove invaluable, especially in regards to the logistical support they could offer. Anything that would help automate a lunar base could prove worthwhile and perhaps fiscally attractive as opposed to being forced to send humans to perform missions that autonomous vehicles could perform equally well. However, as with anything, there are a few ideas that are questionable at best and possibly harebrained or exceedingly dangerous at worst. An example of that is a recent interest shown by scientists and at least one company into the area of utilizing autonomous zeppelins which use hydrogen gas to remain buoyant. The upside, if it works, is that they envision these zeppelins carrying 20,000 tons of cargo. The downside is that they envision using hydrogen gas for buoyancy, which is extremely combustible. Their answer to the safety concerns is to make them operate autonomously. However, the amount of hydrogen required just to lift the cargo without factoring in the weight of the fuel or airship has as much flammable capacity as about 5 million gallons of gasoline. So I can't really imagine either the flight path or landing areas where having the equivalent of 5 million gallons of gasoline burst into flames while dropping 40 million pounds of cargo on everything below wouldn't be considered at least somewhat problematic. Moreover, one of the companies involved has managed to not produce even the first airship in the 6 or more years since providing the media information about their prototype, which has gotten no additional press in the interceding years, thus providing another example of hype regarding something that is supposed to be new and marvelous, complete with catchphrases such as autonomous operation. In fact, that company and at least one more provided CGI animations of what their ideas would look like. But they only serve as cautionary tales of don't believe all the hype that you hear, especially since one of the videos seemed to be more of an appeal to emotion rather than hard science or anything detailing data supporting the project nearly so much as cheerleading for financial backing as a feel-good exercise. However, that brings me to a parting thought. As future decision makers, each of us needs to arrive at our decisions not based on the hype of those who stand to lose or gain from a technology or process being adopted or rejected. We do not need to allow vague notions of a blurry social good or ill to inform our opinions, nor do we need to allow unbridled enthusiasm for what could be to shape those decisions. We need to be mindful of that which is backed by sound reasoning and is not mere optimism run amok. We need to always have the facts or be looking for them because someone else will be depending on us to have them and to make the right decision with them. The future is very bright indeed, but best not to let it blind you to possibilities, good and bad, or into making the wrong decisions out of fear or optimism.